chapter 7, it was probably the shortest chapter we covered for this particular exam cycle because there were really just two main concepts to talk about, and each of them fell under one big category. Chapter 7 really looked to explore the idea further of what a chemical bond is. So, in general, the idea is a chemical bond is some way for our atoms to interact, but in particular, it's how the electrons interact between our atoms. Remember, for example, in the last chapter, we talked about the difference between ionic and covalent bonds. Ionic bonds being when one atom would take electrons from another, in a sense, so that one became negatively charged and the other positively charged, and then they would be attracted to each other. We also had covalent bonds. Those are the ones where we said that the atoms would share the electrons instead, is how we described it. So now what we need, though, is we need a theoretical construct to be able to talk about, so how do these interactions happen? For example, when we're sharing electrons, how do we understand what happens to those electrons? And we have two particular frameworks we can use to talk about this. First, we have valence bond theory. This is where we talk about hybridization. This was the idea that once our molecules start to form, that we keep our atomic orbitals, our s and p orbitals, don't stay so that they're just s and p, but instead they start to combine together, for example, into sp3 orbitals. And we looked at, by using the Lewis structure, being able to predict how would these particular mixings happen. And the reason we were concerned about this was that it helped explain why molecules created the shapes that they did. If you remember right, we had that chart of the different structures you could have for your electrons for everywhere from sp to sp3d2. We look at how they're going to rearrange themselves now that their orbitals have all combined. And in class, we went through and looked at some examples of how if they just stayed as s and p orbitals without any mixing whatsoever, that it didn't create the correct geometrical shapes, that we ended up with different angles than what we actually saw in experimentation. So we had to come up with some framework that said, okay, it can't be as simple as just s orbitals and p orbitals. We'll go over some examples of these, and then we'll spend a little bit of time, although not as much, on molecular orbital theory. This was the idea that a different framework of looking at it. Both of these are just different ways of looking at how molecules, electrons interact with each other and how we form bonds, and they focus on different parts of it. So they end up giving us slightly different pictures of what's happening. And depending on what types of questions we're asking, different viewpoints can be useful and can help focus on particular points that are of interest to us in our particular case. So with molecular orbital theory, the only part we worried about was the idea that, unlike in valence bond theory, electrons were no longer localized. This is the idea that instead of saying the electron, well, it belongs to this carbon or this hydrogen, we instead said, no, these are all spread out throughout the entire molecule. And we're not going to try to designate, oh no, they're specifically from this carbon. We're like, no, they're for everywhere, all over the molecule. And this created a sense of what we call bonding and anti-bonding orbitals to help explain this. We'll look at some examples of that in just a moment, but the general idea was that the bonding orbitals were ones in which, now that the orbitals had come together, these were more stable. This is what encouraged bonds to form. The idea being that because they're lower in energy, it's easier for the electrons to be there. But when we're forming these bonding orbitals, the other orbitals were still there. That wasn't what all of them became. Then we also got anti-bonding orbitals. This was the idea that some of the places where electrons could be found now were actually less stable, and that's why we call them anti-bonding. And so when we're looking at molecular orbital diagrams, we try to see, okay, where are the bonding versus the anti-bonding orbitals, and how does this let us know more about how stable this molecule would be? And this is the main time we use molecular orbital theory in this class, was just when we're looking at different bonds and we were trying to compare, okay, O2 versus F2, which of these is going to have a more stable setup? And we can look towards the molecular orbital diagram to help us figure that out. Okay, so now we're going to look at some examples. We're going to do some hybridization questions. And really, if you can do all these hybridization questions, this is all of the first half of Chapter 7. So if you remember right, though, from class, one thing we have to do with hybridization is we always have to start off with our Lewis structure. So you still have to remember how to do that from the last class. So what I'm going to do is I'm just going to go through and do these examples at the bottom of the page. So we're going to start with CBr4. So if you remember right, we're going to end up with a carbon in the middle, and then we're going to attach it 4 bromines on the end. That's our first step. Our second step from if you remember from the last exam, is we've got to figure out how many valence electrons there are. Carbon has 4, bromine has 7. That gives us a total of 7, 14, 21, 28, 32 valence electrons. So I have 32 valence electrons I need to draw, but we've already drawn 8 because we've got 4 bonds. So that's going to give us 24 total. So remember right, we start by putting them on the external atoms and filling them up to 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so that's our 24 electrons. If we get to that point at the end, we don't have any more to draw, we're done. As long as all the atoms have 8. So we can't draw any more electrons though, right? Once you've drawn all of them, you don't get any extras. You don't get to go, I'm going to throw some more in. So you've got to figure out if everybody's happy. And if not, we'll have to try to rectify that, which we're going to do in some of the later problems. But here we check each bromine has 8 and carbon has 8. Therefore, everything's good. So now we've got to figure out the hybridization. So for the hybridization, we've got to figure out how many electron groups we have. And remember, that's how many atoms it's bonded to and how many lone pairs of electrons there are on the central atom. Don't worry about them on the external atom. We're just looking for this on the central in this case. So carbon has 4 bonds and no lone pairs. So it has 4 electron groups. So from there, we can worry about the idea. There's 2 ways to remember this. One is you could have just memorized 4 electron groups is sp3. And that's our hybridization, and that would be the answer. If you don't remember it that easily, though, you can also write out this thing we showed you in class, right? Where we draw S, P, 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 D, D. Because it's always going to be hybridized in this order for this class. And what we do is we underline 1 for each electron group. So S would be 1, the first P would be 2, the third P would be 3, the fourth P would be 4. And we got to 4, so we were done, so we boxed those. And then we rewrite it just as sp3. Either way works fine. So if writing out SPPPDD helps you, feel free to do that. Or if you just learn 4 electron groups as sp3, that works too. We can also remember that that's a tetrahedral, right? Okay. Now let's look at the next question. So this one, we didn't have any lone pairs, no double bonds, nothing extra to worry about. Reasonably straightforward. Now we're going to look at H2O. So for this one, note that I'm not worried about the way you draw it when you're doing the Lewis structure. I know you've seen water a lot, so if you go ahead and put it in the bent conformation, that's fine. But if you draw it out as a line like this, this is also okay, because initially with a molecule, you're not going to know where the electrons are to know how to draw the shape. So when I'm drawing the Lewis structure, I'm okay if you just put it like this. So, same idea as before. We check how many valence electrons we have. We have 8. That's 6 from the oxygen, 2 from the hydrogens, and we've drawn 4. So we've got 4 left over. Remember, hydrogen was one of our exceptions, and it's the one that is by far the most common to show up, so you need to know that one. Hydrogen only needs 2 electrons, not 8. So both hydrogens already have 2. That leaves us with 4 left over. If you remember right, if we have any extra left over at the end after filling up our external atoms, we will put them on our central atom. So oxygen is going to get 2 lone pairs now, because we've got 4 left over. We then check, and oxygen has 8. Both hydrogens have 2. Everything in this molecule is okay. So now, though, we've got to figure out what's the hybridization. Remember, we both count the lone pairs and the number of molecules it's bonded to. So in this case, we had 2 lone pairs. We had 2 things it was bonded to. We got 4 total electron groups. And from the last problem, this is still sp3. So that is our hybridization for water. You'll notice that even though it looks a lot different than CPR4, it still has that same hybridization. So it's okay to have some molecules that initially to you might look rather different, have a different number of atoms even, can still end up with the same hybridization. What we'll do now is we're going to look at carbon dioxide. So with carbon dioxide, it's going to have the same number of molecules as water, you'll notice. See, in this water, there are 3 atoms, but we're actually going to end up with a different hybridization. And I'll show you how that works. So we have our carbon in the middle, and then it's bonded to 2 oxygens. We're then going to check the idea that, okay, how many valence electrons should we have? 6 in each oxygen and 4 in the carbon. That'll give us a total of 6, 12, 16 electrons. We've drawn 4, so we have 12 left over. So we start putting them on our external atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we've drawn all the electrons. We can't get any more for our system. We don't just get to add extras. But when we go to check, both oxygens have 8, but the carbon only has 4. So we're going to need to get more electrons to our central atom. And if you remember from last chapter, the idea is if you need more electrons on our central atom, we have to form double and triple bonds. Because what it's doing is the carbon's going, I don't have enough, and it needs to ask for help from its neighbor. So, in this case, we're going to take, it needs a total of 4 more. That means it needs 2 lone pairs to help it out. So we're going to grab 1 from each side. Remember back when we did resonance structures, we don't know for sure initially whether it's going to be 2 double bonds or 1 triple bond and 1 single bond. But for the purpose of doing our hybridization, you don't have to worry about it, because all the different structures that we've dealt with so far are all going to have the same number of electron groups. So just draw this one resonance structure, and you can stop at that, because the problem didn't ask you to draw resonance structures. You can do the hybridization with just this structure, and you'll be fine. So now we've got to figure out what our hybridization is. Remember, there are no lone pairs on the carbon, and the carbon is only bound to 2 atoms. So it only has 2 electron groups. This double bond doesn't mean that there are suddenly 2 electron groups per bond. Remember, the double and triple bonds count exactly the same as the single bond. So we only have 2. So you can either just remember that that's sp, or again, we can write out the sp, p, p, d, d way. Box our s and our p, and we're done. So our carbon dioxide, even though it also has 3 atoms, just like water, is sp hybridized. This is why you can't just look at a molecule and count the number of atoms and tell me, oh, the hybridization must be this because there are this many atoms. You actually have to do the Lewis structures. So let's look at another one. Let's look at carbon monoxide. You'll also notice that for carbon monoxide, I mentioned you can do the hybridization for the carbon or the oxygen. This is because they'll give you the same answer, and it doesn't really have a quote-unquote central atom because there are 2. And as you know, the center of that, there wouldn't be something in the middle of that. There's no atom there. So let's look at carbon monoxide. So we start with CO. It should have a total of 10 electrons, and we've drawn 2. That'll give us 8. So I'm going to start filling them up, and it doesn't matter what order you do this in because it's going to turn out the same in the end. So I put 6 on the oxygen, 2 on the carbon. Now, as we mentioned last time, both oxygen and carbon want 8, but we only have 8 on our oxygen, but 4 on our carbon. So carbon is going to have to ask oxygen for help. If carbon tries to help oxygen, it's not going to help out. You'll just end up with extra electrons on the oxygen. So that's why I know that the extra ones have to come from the one with 8. And since I know carbon needs 4, I'm going to need to do 2. I've got to share 2 pairs because each pair is going to help me by adding 2 electrons. So since it needs 4, we need 2 pairs. So this gives me a triple bond with 1 lone pair on the oxygen, 1 on the carbon. So we can, again, figure out the hybridization. There is 1 atom that the oxygen is bonded to. I'll just do it for oxygen. And then there's 1 lone pair. So you add this up, you get 2 electron groups. Carbon monoxide also has an sp hybridization just like carbon dioxide did. Okay, hopefully that feels all right. So now what we're going to do is we're going to look at a molecule that has more than 4 atoms bonded to it to see if we can remember how to do those hybridizations. So we're going to look at SF6. So we have S, and then we bond it to 6 fluorines. Remember, I'm not too concerned about exactly how you draw this. It's okay if yours doesn't look exactly like mine does, as long as there are 6 fluorines connected to 1 sulfur in the middle and no other bonds to the fluorines. So again, we've got to figure out how many electrons we're going to have. Each fluorine is going to provide 7, and there's 6 of them. So that provides 42, and then the sulfur is going to provide 6 more. So that is going to give us a total of 48. So we want 48 electrons, and we've currently drawn 2, 4, 6, 8, 10, 12. That is going to mean we need 36 more. So we start by adding electrons to each of the fluorines, and each of these is going to need 6 more to get to its total of 8. And you may notice already that since I'm adding 6 to each of these, that since there are 6 of them, that's going to amount to 36. So I'm going to end up with exactly enough, with no double bonds needed to be formed and no extra lone pairs to have to drop on the sulfur. So for this one, we're going to end up with this setup where we've got 6 atoms bonded to our sulfur and no lone pairs. So our electron groups, we have a total of 6 electron groups and no lone pairs. So that gives us 6. You can either just remember that 6 was sp3d2, or again, you can draw out your setup of S, P, 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 D, D, and underline 1, 2, 3, 4, 5, 6, and you end up underlining 6 letters, and one of them is an S, 3 are P's, 2 are D's. So you can then rewrite this as sp3d2. I shouldn't have boxed the whole version up there because the actual answer, you still need to reduce it down to this sp3d2. You won't see it written as sppppdd as a final answer. Okay, we've got 2 more to do now for our hybridization. So let's look at 2 more examples. We've learned all our rules now, so this is mostly just going to be examples in, okay, do you remember how to draw your Lewis structures? And then remember how to do that, just one little extra step. So we have ICl2. So we've got 2 chlorines bonded to our iodine in the middle. We should have a total. Oh, did I do ICl2 on here? This is a question that I needed to make different to be able to make it more reasonable for you to do. I will fix this in the future iterations of this. I actually wanted to ask you to do ICl3. And the reason for this is this has an odd number of electrons, and we haven't dealt with how to deal with, okay, discard the ink. We haven't dealt with how to deal with odd numbers, and we're not worried about that for this course. So I'm going to go ahead and just do ICl3. Sorry if you were working on it before and that took you a lot of effort for that. But no, we're not going to have to worry about the odd ones for this class. So I'm going to put 3 chlorines on my iodine, and I don't care how you rearrange them. We should have a total of 28 valence electrons. And from there, we're going to have that we subtract out, we've currently drawn 6. So we are going to need to put 22 more electrons on there. So I'm going to start by adding them to the external chlorines. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. You've noticed I've drawn 18 electrons. I still have 4 left over. And as we said, those all have to go in our central atom, or iodine. So we add 2 more lone pairs there. We now end up with 3 things that we're bonded to, plus 2 lone pairs. We get a total of 5 electron groups. So we rewrite out our SPPPDD. We underline 1, 2, 3, 4, 5. We're going to get sp3d. And that's going to be our hybridization for our ICl3. So just 1 more to do now. We're going to do PCl3, and then we'll be done with our hybridizations. So we have our phosphorus bonded to 3 chlorines. You'll notice this looks a lot like the initial one, but now we have a different number of valence electrons, because now we have 7, 14, 21. We've got 26 total, and we've drawn 6. So we need to put 20 more on this molecule. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We've got 2 left over, so we just have to put 2 on our P. So now we have 3 atoms we're bonded to plus 1 lone pair. We get 4 electron groups. So this is going to be sp3. You'll notice it's the same hybridization as our ones up at the top of CBr4 and H2O, even though it only has 3 atoms this time. So if you can do these, you're set for trying to do hybridizations. You'll notice it's mostly just draw a Lewis structure, plus remember this extra step we have to do with it. The only other thing I'll mention is make sure to go back to your notes and look at, so what do we mean, where do these hybrid orbitals come from? The idea being is that they're a mixing of atomic orbitals. That's where we got things like, okay, I can figure out if I have an sp, that means I've got 1 s and 1 p orbital added together. And then I've got 2 p orbitals left over since those other 2 don't get mixed together. Just go back and look at that a little bit to make sure you're okay with conceptually, what do I mean by an sp3 orbital versus an sp orbital? Okay, let's go to our next slide. So now we're going to look at a different way of looking at this. We're going to look at molecular orbital diagrams. Note that what you see drawn on the right here, I'm always going to, for this class, I'm always going to let you, I'm not going to make you come up with these sigma stars, pi stars, and all that. I'm going to go ahead and give that to you as I'm not worried about to figure out the exact difference between these. Okay? You're going to just go with, okay, that's how they particularly mix together. Because we don't really covered enough yet the concern of, okay, how do I know that there should be a pi there, or a sigma there, or why is it that it's drawn this way versus some other way? So what we do is we think of this as the stuff on the left and the right is the atom before it's mixed together into a molecule. So for example, let's say we're going to look at O2 first, because the problem asks us to look at O2 and F2. The stuff on the left and the right are like separate oxygens before they've been mixed together. So let's try that out. So oxygen by itself would have 6 valence electrons. So we're going to put 2 in our 2s, right? Because 2s is lower than energy in 2p. We're then going to go into the 2p and go 3, 4, 5, 6. And we'll end up with 1 lone pair together and 2 electrons by themselves that are both the same direction, in this case pointing up. We'll do the same thing on the right. We do it with 1, 2, 3, 4, 5, 6. Okay. So now we have a total of 12 electrons, 6 from each oxygen. And when we mix them together, we don't worry about where they're coming from. We just say, okay, we've got 12. And we're going to use the same filling rules we did for atoms. We're going to start at the lowest energy and go up. So here, we're going to start at the bottom and go 1, 2. Then we go to the sigma star 2s, 3, 4. Then we're going to add some more, 5, 6. Then we get to the pi 2p. You'll notice there are 2 orbitals here that are equal in energy. They are degenerate. That means we start with them unpaired. That'll be our 7th and our 8th. But then we start to pair them again once we've done all the ones we can unpaired. So then we have 9, 10. We're then going to add 2 more, this time to our pi star 2p. That'll be 11, 12. So let's try figuring out, so the question asks us to draw both O2 and F2. So that I don't have to redraw the entire thing, I'm going to go ahead and answer some of the rest of the question, and then we'll go back and do it for fluorine. So the question asks us to calculate the bond order for oxygen. So I'm going to do this over on the left. So O2, the bond order for it, I'm going to write it like this. Bond order, BO, of O2. It's going to be equal to 1/2 of our bonding electrons. And if we go over here, you'll notice there are 2 bonding electrons in the sigma 2s, 2 in the sigma 2p, and 4 in the pi 2p. That gives us a total of 8 bonding electrons. And we're going to subtract from this the anti-bonding. There are 2 in the sigma 2 star s, the sigma star 2s, and 2 in the pi star 2p. So that's going to be 8 minus 4. We're going to end up with 1/2 of 4, which is going to be equal to 2 as our bond order. Now, let's try figuring this out for fluorine now. So I'm just going to go back to our diagram, and we're going to replace the O's with F's, and we're going to talk about how this would change the system. So let's say instead we had 2 F's and then F2. So fluorine has 7 valence electrons. That means it's going to have a total of 7 in the 2p, which means I would add 1 more electron to my 2p that is going spin down to pair up with the spin up. We then added 2 more, so you need 2 more electrons in your molecular orbital in the middle. So we're going to put, don't do that. We'll put 1 going down here, 1 going down here. We can then calculate the bond order the same way we just did, but now we have 2 more anti-bonding orbitals. So now we can do bonding order of F2 is equal to 1/2 of, we still have the same 8 bonding electrons, but now we have 6 anti-bonding, and we get a bonding order of 1. And if you remember right, that also tells us that the fluorine bond isn't going to be as strong as our oxygen bond according to this diagram, because our oxygen is a higher bond order. That means there are more bonding electrons for the oxygen, and that there are fewer bonding orbitals, bonding electrons for our fluorine. Well, fewer net bonding electrons, right? There are still 8 in both of them, but there are more anti-bonding in the fluorine, which can help to cancel out some of the effect of the bonding electrons. Then there was one last question, which was to now try to do this with neon, and to specifically ask the question of how likely are we to find diatomic neon. So I'm going to do the same thing I did here, just so I don't have to redraw the entire thing. Now let's look at what neon and neon 2 would look like. So neon has a total of 10 valence electrons. So we've got, or 8 valence, 10 total. So we've got to put another electron in our 2p. So now the 2p is entirely filled. That means we've got 2 more. So we've got to put them in the last place we have available, which is our sigma star 2p. You'll notice now if I calculate the bond order for neon to diatomic neon, we get that it would be 1/2 of 8 minus 8, which would be equal to 0. And if you remember from class, we said that a bond order of 0 meant that we weren't going to find that bond because it wasn't any more stable. Because the anti-bonding orbitals were just as commonly filled as the bonding orbitals, means there's no extra gain to have this form a molecule like this. So, if you can do this, this is most everything we're worried about with the molecular orbital diagrams, right? We didn't spend as long on these, but I do want you to be able to do them. It was be able to fill these up from bottom to top, understand what we mean by a bonding and an anti-bonding orbital, and be able to calculate a bond order and tell me something about the likelihood of that molecule forming compared to others. Or to be able to tell me something about the bond strength if I were to compare 2 bond orders of 2 different molecules. We also did some easier examples in class, which you can go back and look at in the notes, of just things like hydrogen and helium and what happened there when we were looking at the difference between diatomic hydrogen versus diatomic helium. I'd suggest if this doesn't work so well, go back to the notes and check out those examples. So, oh yes.